Okay, so for chapter 7, we're going to be learning about the atomic structure, electrons, and this term periodicity. I don't really like that term. Basically, we're learning about electron behavior and things about energy and quantum models and the Bohr model. So basically, we'll start off with electromagnetic radiation, so EM radiation. And I'm sure many of you have heard of EM radiation, but basically, it's light. So we know the most observable form of EM radiation to us is visible light. So the photons that are, we know from physics, they are particles and waves. So they behave like waves and particles at the same time. They have this particle-wave duality, is what is a key feature of electromagnetic radiation. Now, this electromagnetic radiation can take the form of different things. So we see visible light as like the sun, light that comes out of the sun, but also in the sun, there are other rays, things you cannot see, such as UV radiation. And there's also gamma rays and different nuclear things that come out of the sun that are really high energy, high frequency radiation that we can't observe, but we can observe the effects of it on other things. And in a vacuum, all EM radiation, whether it's a radio wave, visible light, or an X-ray, travels at the speed of light, which is 3 times 10 to the 8th meters per second. So we call it 2.99, whatever. You could just say on exams, 3 times 10 to the 8th meters per second. And there is 2 key traits of every type of electromagnetic radiation. It has a wavelength and a frequency. So a wavelength is the distance between 2 peaks in the wave. So what that means is, let me get my pen out. So what that means is if you were to put the wave frequency on a graph, and it would look like that, like a sine wave, cosine wave, that's a wave. So the wavelength is the distance that it takes to go from peak to peak. So that's the wavelength. And it's usually measured in, it's a distance, a physical distance, and it's nanometers. We can measure it in meters, but usually it's in the hundreds of nanometers. For a lot of for visible light, UV light, even X-rays, it's lower nanometers, but like maybe a couple hundred. And then for frequency, so frequency is a number of waves per second that go through a point. So it's not necessarily the speed. So frequency is, for example, this is one wave. A wave that would have a higher frequency would be this. Because in one, imagine all these waves are moving to the right at the same speed. The time it takes for one of these bigger waves to go through, let's say it takes a second. In that 1 second, how many of these ones have gone through? Assuming they're all going at the same speed, which is the speed of light. So imagine they're going towards the right. Then if you look at the higher frequency radiation, the higher frequency wave, in the same amount of time that this part peak to peak of the lower frequency radiation goes through, already 1, 2, 3, probably 4 or 5 waves of the lower frequency one have gone, or of the higher frequency one have gone through. And you notice that in this higher frequency wave, the only way for it to have higher frequency and have the same speed, meaning the rate at which these waves move across the time-space, is if the wavelength is decreased. If I had another wave here with the same wavelength, it has to move at the same speed, because you cannot change the speed at which this frame moves across the page, because that would be changing the speed of light, which you can't do. You can't increase it, but you can certainly decrease the speed of light. But that's why they make it careful to mention that all the EM radiation travels at the speed of light in a vacuum. That's specific. If you have it in different mediums, such as water, light travels slower in water, because if you could observe that, if you put your hand in the water, it looks like your hand is disjointed from your rest of your arm a little bit. It looks like it's shifted over. That's because of diffraction. And that's because the light actually moves slower through the water, and it causes a diffraction pattern. But that's a different thing. So anyway, the main point here is that the wavelength, which is a physical distance of the wave, is inversely proportional to the frequency. meaning if one goes up, the other one has to go down in order to keep that same speed of light. So they're inverse. Now, what that means is when you put them into an equation, you get this. That's exactly what you get, kind of like any inverse relationship we talked about in this class, such as Boyle's law, and even like, yeah, I guess Boyle's law is the main one, PV, right? So we have another direct or inverse proportionality where the wavelength times the frequency equals c, which is the speed of light. So c is our speed of light. This v is not really v, it's nu. This is the lowercase letter for nu, lowercase Greek letter nu. Capital Nu is just a big N. So this means frequency. So and it's measured in cycles per second. So it's not necessarily speed, it's not meters per second, but it's just cycles per second. So how many of the waves go through per second? So, and you measure this, the unit is actually seconds to the -1. And then the wavelength in meters is just in meters. This always has to be in meters. And then if you multiply these together, it makes sense that meters times 1/seconds equals meters per second. That's why it all has to equal the speed of light after you multiply it. So next is the classification of our EM radiation. So here's the entire EM spectrum that we know of. And in the small middle section is the visible light, the light that we can see. And that visible light goes from violet all the way to red. So like Roy G. Biv. So red, Roy G. Biv. R-O, orange, yellow, G is green, Biv, which is blue, I, which is indigo, and V, which is violet. So if you say it backwards, you usually in high school, at least I learned Roy G. Biv, which is basically all the colors in order, going from high wavelength to low wavelength. So one of the key things about understanding this EM radiation is understanding that wavelength and frequency are inversely proportional. So for example, violet, which happens to be a higher frequency visible light, the highest frequency, so put high frequency, tends to have the smallest wavelength. So this chart goes wavelength in meters. This one has 4 × 10⁻⁷, or 400 nanometers. If you go all the way to red, red has a low frequency for the visible light. And it has 7 × 10⁻⁷ meters in wavelength. So that means the wavelength, which is lambda. I didn't talk about that Greek letter at all. But yeah, so wavelength is lambda. So that's what that Greek letter is. Anyway, so in a radiation like red, where the frequency is low, the wavelength would be high. It would be a relatively longer wave, because in each one of those propagations of the wave, it would be slower and less cycles would go through per second. So that's why our frequency would be lower. And on the other hand, violet, which has a high frequency, will have a small wavelength, meaning that many of those smaller waves propagate per second, making the frequency higher. And then you have a whole spectrum in the middle. So you notice how the visible light is just a small little carving of our knowledge of EM radiation. This is just what our eyes can see. Some animals, like bees, for example, they can see some of the UV radiation, which is right here, ultraviolet. And you notice that if you get a higher frequency than ultraviolet or a lower wavelength, you get to ultraviolet. And then going the other way, if you go a lower frequency or a higher wavelength from red, you get infrared. So that's why they named those that, the ultraviolet and infrared. That's why they named them like that, because where they occur. And then if you go towards higher frequency, you get to X-rays and gamma rays. So here's an important thing. So the frequency is proportional. Here's the proportional sign. Proportional to energy. Meaning if you have a higher frequency radiation, it's going to have a higher energy and it's going to hurt you, or be more likely to hurt you. So that's exactly true. UV rays, we know they can cause skin cancer if we don't wear sunscreen, right? So it can penetrate your skin cells and actually damage the DNA. So it's harmful to us because it has high radiation or high energy that can get through and penetrate clothing and skin. Well, not really clothing, but can penetrate skin cells. X-rays, we know we can only limit ourselves at the dentist to a certain amount of X-rays per year, maybe one or none, or one every couple years. And when we do get an X-ray of our teeth, what does the dentist do? They put a big lead heavy smock on you. That's to block the X-ray radiation from going into your chest or going anywhere vital. So the X-rays are higher frequency. So they're higher energy and they can hurt you more than UV rays. So that's also dangerous.
But again,
Where?
right there, and I circled it again, and you still didn't like that one.
Okay. So then gamma rays are the highest frequency radiation that we know of, and it's very dangerous. So the gamma rays are what was released in any kind of nuclear disaster, which gives people cancer and kills them. Nuclear bombs like Hiroshima, Nagasaki, Chernobyl, things like that, Fukushima, nuclear disaster, things like that release gamma rays because I mean they're very high energy and they can go right through your body really, and they can give you cancer at a higher rate than X-rays can, but they're all very deadly in this range. And then when you go towards infrared and go to the other direction where you have a longer wavelength and a smaller frequency, you get to non-harmful, such as microwaves, radio waves, AM, FM, and whatever. But now you notice something, that microwaves aren't harmful. They're in the non-harmful area. That's interesting because a lot of our parents, including mine, told me, my mom used to tell me, don't stand in front of the microwave when the popcorn, blah, 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 because you can get cancer or whatever. That's BS. That's bullshit. Because microwaves, according to science, they can't penetrate your clothing. They can't penetrate your skin. They can't affect DNA. So microwaves are basically safe. Just don't stick your head in a microwave because they do get really hot, but they're safe in terms of the radiation themselves. They're in terms of the particle wave duality of microwaves are safe for your body. And so is infrared, and so is the visible light. And radio waves, same thing, they're very safe. They've been around for hundreds of years and no study has concluded their effect on anything. And I'm sure a lot of you are thinking, what about cell phones? Where do cell phones fall? Cell phones fall, I think, about in between infrared and microwaves. So that's where people come up with this pseudoscience that, oh, cell phones, if you sleep with it next to your head, it can cause brain cancer because the radiation emitted from cell phones to the tower is on the same spectrum as microwaves. But that's not true either because, I mean, that part's true, but the fact that they can hurt you is not true. So there's no conclusive evidence that cell phones lead to any kind of cancer. And as a male, people used to tell me, I used to hear in school, oh, don't have your cell phone in your pocket because it can lead to reproductive problems in terms of fertility and things like that. But that is not true either based on scientific studies done. So we can take a big sigh of relief, at least for now, until like iPhone 12 maybe has some hidden cancer radiation. Who knows? When the cell phones get better, they might get more dangerous. Who knows? With 5G and everything. But right now, not so much of a danger. Okay, cool. Next, we're going to do some practice. So if you have red colors seen in fireworks, do the emission of around wavelengths of 650 nanometers when strontium salts are heated up. So calculate the frequency of the red light of the strontium when it burns. That is 650 nanometers or 6.5 times 10 to the 2 nanometers. So we're calculating frequency from wavelength. So you guys need to be comfortable with going back and forth from frequency to wavelength. And here's how you do it. So we're starting out with the equation that the wavelength times the frequency equals the speed of light. And we can rearrange that equation any way we want. We can say that frequency equals the speed of light over lambda, or we can say that lambda equals the speed of light over the frequency. And then we can just plug in our values. But we have to make sure our units are correct. Because sometimes they like to give us wavelength in meters, and we have to convert it to nanometers by multiplying by 10 to the negative 9. And I'm just seeing your comments now. Brandon, yeah, 5G. Who knows? That's what I said. I didn't look at any papers on that yet, but that is a big topic right now. But yeah, I kind of answered that inadvertently. I don't really know too much personally about it, but we'll see. We're the test monkeys for that. I still have a 4G phone. I'll stick with my Google Pixel 2 for now. It's a beast. I love this phone. But anyway, So to solve this, to find the frequency, we would use this frequency equation. Either one of them is fine. And then we put in C as 3 times 10 to the 8th. And then our wavelength, 6.5 times 10 to the 2nd. And we would come up with our answer, which is in hertz. So this unit of per second, which is the amount of wave propagations per second, that is also measured in hertz. So that's the same thing. Per second is the same thing as hertz. So with these EM radiations, it's going to be a lot of hertz, 10 to the 12, 10 to the 15, things like that. Because if you think about it, our wavelength is going to be something 10 to the negative something, usually 10 to the negative 9, 10 to the negative 7, or sorry, it's going to be, well, it's going to be, this is nanometers, we need to make it meters. It's going to be 10 to the negative 7 meters, right? And our C is going to be 10 to the 8th. So 10 to the 8th divided by 10 to the negative 7, that's going to be a big number, something like 10 to the negative 15. So our answers for our frequency are always going to be in the realm of 10 to the negative 14, 10 to the negative 15. So if you see those high numbers, don't be alarmed. Just letting you know. Okay, so which of the following forms of EM radiation has the shortest wavelength? So somebody can answer this if they want, if they remember. Good, A, nice. So, and we're going a little bit faster because we don't have much time. I don't want to get through half of it, but I want to get through probably a little bit more than a third. I know you guys had a rough day with the exam, so a lot of this information is just formulas and background. So so good job, Harrison. We have gamma rays have the lowest wavelength, and they have the highest frequency. So that's important to make that distinction. So shortest wavelength, the same thing as highest frequency. So yeah, gamma rays. Good. Okay, moving on to the next thing. So the energy of any of this electromagnetic radiation can be determined. Now, we can determine the energy of any photon of any type of EM radiation, thanks to this guy Planck, Max Planck. So when I think of Max Planck, I think of, if you remember Ed, and Eddie, they had that Planck with the smiley face on it. That's what I think of when I first heard of him. But anyway, he's a scientist and he's a lot smarter than that piece of wood with the face on it. So he postulated that energy can be gained or lost in whole number multiples of his calculated constant, which is Planck's constant. Basically, the energy in a photon, depending on the photon's frequency. And this constant will be given on the exam and is 6.626 times 10 to the negative 34 joule times seconds. So joule seconds. And for now, not much more explanation on that. Just that's the constant. And it's used to represent heat or energy of a photon. And that goes into the equation of the energy of the photon, which is pretty simple. Delta E equals N times Planck's constant times the frequency. So N is an integer. If you want to find the energy in one photon, N will be 1. If you want to find the energy, and this question might be given on homework and exams, finding energy of a mole of photons of blank frequency. In that case, you'd make N equal to 1 mole, meaning 6.2 times 10 to the 23rd. You'd have Planck's constant in there, and you would have the frequency. So the frequency would be in terms of hertz, or 1 per second. And then that number should be in the order of 10 to the 14, 10 to the 12, something big. So using that equation, we can say that energy is quantized in units of HV, meaning that for every photon of a certain frequency, we have an energy packet unit called HV. And this is called a quantum of energy. We hear this word quantum being thrown around a lot, but it's first derived from quanta, which that's where this science emerged from, a quanta of energy. So the reason why we call things quantum is because it's a really abstract concept. Like photons, they don't have mass. So kind of like E equals mc squared, oh, energy relates to the mass. Well, in this case, it doesn't, because we're moving at things at the speed of light where mass doesn't really have an effect. So we have this quanta of energy, which is represented in photons by this Planck's constant times the frequency. And that's just all we can say about that without getting super into physics. If my ex-roommate was listening right now, he's a physics major, so he would be like technically what you just said is wrong because blah, 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 blah. But I mean, whatever, Chem 1, basic explanations. Because he even said like even the basic explanations that we teach in physics are technically wrong because of a lot of the graduate classes he took. But whatever, I mean, the basics are the basics. And they help us find the answer on the exams. That's the most important thing. All right, so let's do another example. So a blue firework is often achieved by heating copper chloride to about 1200 degrees Celsius. And you notice this is the second question we had with fireworks. So before we get into the Bohr model, which is a key concept of understanding atoms and how all this information, which seems to be a little bit different than chemistry, goes into atomic chemistry, which we're used to, is that when you heat these metal salts, what happens is the electrons in the salt or in the metal really will hop energy levels. They will actually go from their ground state energy level and they will increase in their energy level. When they come back down to their ground state, they release energy in the form of light. That's how fireworks work. You heat up the metal, they excite their electrons for only momentarily, very transient, very quick temporary interaction. Electrons will jump, then all their electrons will jump back down. When they jump down, the energy from the higher energy level to the lower energy level has to go somewhere. And it so happens that it is emitted in the form of visible light. And that visible light color depends on the type of metal, whether it's copper, which would make blue, and also copper solutions tend to be blue. But other things like sodium is orange, for example. But yeah. So let's say we have a compound that emits blue light, has a wavelength of 450 nanometers. What is the increment of energy, meaning the quantum, that is emitted at 4.5 times 10 to the 2 nanometers of copper chloride? So first we would figure out our frequency. Since frequency, we can have our wavelength, that's all we have. And a lot of these questions, you're going to be given wavelength. The first thing you should do, and the first thing you can do, is figure out frequency. So we can figure out the frequency. Then we can put that frequency into Planck's equation by h, which is Planck's constant, times the frequency we just found, to figure out the energy or the quanta for that type of radiation. And you multiply those two numbers together, and you get 4.41 times 10 to the negative 19 joules. So a lot of these questions use both of those equations. So if you want to quick figure out the wavelength, quick figure out the frequency, you get that. Then you can use that to find the energy of that photon or a number of those photons using Planck's equation. Wait, when solving for frequency, why are you not using 1 over lambda? It's C over lambda. So Harrison, now, yeah, it would be the equation C over lambda, if that's what you mean. So that's why we'd use this equation. Okay. They're inversely proportional, yes, but their inverse proportionality equates to something, equates to a constant, which is C. Okay, so Einstein, he was a really smart dude. You've ever heard of him? So basically, we kind of know this already. I mean, you can modify Planck's equation, and then instead of frequency, you can put in the expression for frequency, which is C over lambda, and you get hc over lambda of the energy of the photon. Basically the same thing. He kind of took Planck's idea and just said, like, he spruced it up a bit. Same thing. But he also talked about this effect, which is the photoelectric effect. Now, and this is important. I mean, you guys have to do math on it. I don't think you have to do equations on it. I think only 125 does that, but you have to know what it is. So the photoelectric effect, it is a thing that happens, and it's the reason why, since we talked about microwaves already, it's the reason why if you accidentally put tinfoil in the microwave, it starts sparking almost immediately. So what happens is, if you have a metal surface, and that metal surface can differ. It could be strontium, it could be sodium, it could be tin, whatever, aluminum. If you have low frequency radiation hit it, nothing will happen. Low frequency radiation meaning visible light, infrared, radio waves. If you put tin foil on your table, it's not going to spontaneously burst into flames and spark, right? That's because you have low frequency radiation that's constantly hitting it. And even UV rays are low enough where it doesn't do the photoelectric effect doesn't happen. When you have high frequency radiation, such as, well, actually that kind of contradicts, because microwaves, hey, professor, aren't they low frequency radiation? Why do they cause the photoelectric effect? Good question. Because over time, and you notice that it takes a couple seconds for the metal to spark. That's because the metal surface is small. Let's say you mess up and you try to take all the tin foil off and you accidentally put a little sliver of tin foil in the microwave. The smaller the tin foil, the shorter time it would take for it to spark. That's because that amount of energy is compounded on itself when you expose the metal to higher frequency or even lower frequency radiation for an extended period of time. And the microwave itself is very concentrated microwaves. So over the course of a few seconds, those concentrated microwave energy would build up and cause the photoelectric effect. And what the photoelectric effect is when you do have enough frequency hitting a metal, it can actually kick off an electron or more electrons. And usually it's one photon of high enough energy kicks off one electron. Usually we assume that. I'm not sure if it's actually true. I think it most of the time is true, that it's usually one photon to one electron. So the idea is, and we can put it in math terms, that there is a minimum energy that's dependent on the type of metal that is required to remove the electrons from that metal by any kind of energy source. It doesn't have to be EM radiation, but the photoelectric effect specifically talks about EM radiation in terms of high frequency radiation or low, but it can be any type of energy. And in the microwaves case, the frequency kind of isn't there. It's a lower frequency, but the amount of energy compounded over time is more than enough to knock off the electron. So we can say that the amount of energy needed is this E0, and it equals Planck's constant times the frequency, the minimum frequency required. So this is what I mean when I said before that the frequency is proportional to the energy, and they're proportional by Planck's constant. So that's a thing to know. But here's what happens. When the amount of frequency, or sorry, not amount of frequency, when the frequency of the radiation is higher than the minimum energy requirement, or higher than the frequency required for the minimum, then that excess energy removes the electrons and gives it kinetic energy. So, and it removes them with a certain speed. So this threshold point, that's exactly what it is. It's a threshold. So it's saying at a threshold frequency of the metal times Planck's constant equals the threshold energy needed to remove that electron. Anything above this will remove the electron. Anything below this will not. So what happens is, with a microwave, in the first 2 seconds, if you have a large sheet of tinfoil, this energy quotient product will not be high enough, E0 will not be greater than E0. But if you give it a few more seconds, it'll build up and it will surpass E0. Then this happens. Not necessarily in the microwave's case, not the frequency, but the energy would be exceeded. The minimum energy required would be exceeded, which then means that electrons can be removed and be pushed out of the metal with a certain speed and kinetic energy. So does that make sense? I know it's a lot. And you can, I think that was a good explanation, but you can listen to that again on the video. I just went on a little mini roll right there. So that was good. But yeah, photoelectric effect. Now, what you can do with the photoelectric effect, which I don't think we're going to be covering, is we can actually calculate the minimum energy requirement based on the speed of the electrons emitted, or the energy at that they're emitted by, also the energy and frequency of the incident photon. And we can just do some subtraction and we can figure that out. We can figure out the minimum energy required or the amount of energy remaining, or even answer questions with certain parameters. Will the electron be emitted from the metal, or will the photoelectric effect happen? We can figure these things out. All right, so moving on to the atomic spectrum of hydrogen. Now, hydrogen is the simplest molecule that absorbs energy, and it absorbs energy and creates a spectrum after that energy is released at a lower frequency. So we can deduce the line spectrum from that. And here's basically what it looks like. So if you put some kind of light, let's say it's high, you put really any kind of light through a slit and then put that through a prism, it will split the light into its spectrum. This is a continuous spectrum. And that happens with really like sunlight, you can do that with most types of light, you can do that. But if you have a specific light that only contains, let's say it's a neon beam, let's say it's an argon beam, or it's a combination of, you know, those neon beer signs? That's a combination of neon and argon usually, and even xenon sometimes. Because if you mix those in certain ratios, you get different colors. Like the neon signs, they're not all neon. Some of them aren't neon at all. For example, the blue ones are almost exclusively argon. So that's a fun fact. But regardless, if you only put in specific beams that are 1 or 2 elements, you won't get a continuous spectrum. You'll get a line spectrum. So the line spectrum looks like this. And for hydrogen, it only has 4 lines. It has one at 410, which is like violet, one at 434, which is indigo, 486, which is a lighter blue, and then 656, which is orange. So why does this happen? And it happens because of electrons. And keep in mind, this is for hydrogen. Hydrogen is the simplest of atoms. Has 1 proton, 1 electron, and it's not nearly as complicated as the other ones. So what happens is that how does it say it? The changes, what do they say? They say the change in energy between, oh, I guess so. Yeah. So basically what happens is, let's look at the diagram again. You notice that it says high voltage here. In order for this light to glow, there has to be some kind of energy or a voltage, in this case a voltage, put through the hydrogen sample. In this case it's a hydrogen gas sample. For that energy to be put through, what it does is, like I said before for the fireworks, this is basically what I explained with the fireworks, is that it makes the electrons in hydrogen originally from the ground state, and they jumps them to a higher energy level. But this only happens momentarily, because think about it. There are many, many hydrogen atoms in this tube. So if one of them gets excited and then moves away, quickly it goes back to ground state. And this happens with billions of them. So you can imagine that a lot of them are just quickly going up and then going down, up, down, up, down, up, down. And when the electron goes from up to down, meaning a higher energy level to a lower energy level, there is a form of light released. And visible light is usually one of these colors. And it could be, and for hydrogen, it's a combination. So some of the electrons go up maybe 2 energy levels. Some of them go up 1, some of them go up 3, some of them go up 4. But depending on how much energy they have or how much energy they're excited by, when that electron comes back down to ground state, that is associated with the energy of visible light, or the frequency of visible light that's released from that process. So does that make sense? Basically what happens is, I'll draw a little diagram. You have hydrogen, there's the nucleus, there's electron, there's before, and then you heat it up. I'll put arrow, and I'll put flame. This is a flame, O2. What happens is, this is energy level 1. That's what the electron originally was. This is energy level 2. So electron jumps to energy level 2. And then we'll put 1 nanosecond goes by. Then what happens is that electron will come down again. It will come down. Once it comes down, so going from So here, this is what we mean by absorbing energy. The hydrogen in this case absorbs the energy because the heat leads to an increase in energy level or an increase in energy of the electron, which means it momentarily absorbs energy. But that's a quick interaction. Once the electron returns to ground state, that energy that was absorbed has to be emitted. And it's emitted in the form of visible light with the frequency. Now, the amount of energy gained, here's another fun fact. The amount of energy gained by the electron from going up is not exactly the amount of energy released in the photon in this step. And that's because in this process, there is some energy lost. So where is it lost? In the micro interactions and vibrations of the electrons. Micro interactions isn't a real word. I just made that up. But really in the vibrations. There's a lot of vibrational states, like a really real quantum physics phenomenon that are going on in this process, which then leads to a reduction in energy. But it's a small loss. But most of the energy is re-released when the electron comes back from its higher energy state to its lower energy state. Okay, so which of these following statements is false? Energy of electromagnetic radiation increases as the frequency increases. What do you think? Don't tell me you guys fell asleep already. True. Good. Good job, Harrison. So yeah, we talked about how, and good job, Catalino. B is false, but A is true because we know that energy has a direct proportionality with frequency. Frequency increases, that means the energy is higher and more dangerous. For B, an excited atom can return to its ground state by absorbing electromagnetic radiation. That's false because when the atom gets excited, that's when it absorbs energy. When it returns back to ground state is when it releases the energy that it had just absorbed, or most of it. So that's why B is false. Okay, so we'll take a look at the quantum model real quick, and then we'll go over one equation, and then we're done. So here's the Bohr model, which is basically the thing I tried to draw in the egg yolk that I tried to draw. Basically, you have the nucleus is in the middle, and in hydrogen's case, you have one electron, but in more complex atoms, you can have electrons residing at different energy levels. And we'll learn more about these energy levels and become very accustomed to figuring out not only the energy levels, but the subshells within the energy levels next week. So for example, in energy level 2 or energy level 1, I guess this is 1. This is 1. So I guess this is 1. So wait. I think this is 1. So in 1, you have a total of 2 electrons. In 2, you can have a total of 6 electrons. Yeah. Well, technically, you have 2s, 2p. So you have 8 total. And then in 3, you'll have a total of 18. But we'll talk about that later. So these electrons in more complex atoms will jump multiple energy levels. And there'll be a whole range of electrons that will jump a certain amount of energy levels and come down in a certain way. When they come down, they all come down. Basically, there's a lot of stuff going on. When the thing I just said with hydrogen happens for these complex atoms, you get a whole light show. You get the line spectrum will be a lot more complicated. And are there any ones shown here? I don't think so. But some of the light spectrums could have, well, the heavier atoms that have more electrons to move can have 10 or even 20 different lines. So the more complex the atom and the more electrons it has, the more lines it has in its line spectrum. Okay, so here's something that the Bohr model states, and this equation will be given on the exam. So basically, we can calculate the energy for an electron at a certain energy level of an atom. And we can also calculate in this process of the energy, of the electron returning back to its ground state, we can actually calculate how much energy that is and what the frequency of that energy is, and even characterize that energy as some type of light. But professor, how can we do that? It seems really cool. Well, here's the equation. And this is Bohr's equation. So it's E equals negative 2.178 times 10 to the negative 18 joules, which is just a constant derived by the electron, by the charge of an electron, or by the energy of an electron. And times z squared. So z squared is the nuclear charge, basically meaning the number of protons or the atomic number. So the nuclear charge divided by n squared, which is n is an integer based on the energy level. And the energy level varies. So wait, is there an example? Yeah, so basically what we can do is we can say that the energy of the electron in its final state minus the energy of its electron in the initial state is the change in energy from going from the excited to the grounded. So by final state, I mean after it's grounded, the initial state is when it's excited. So in that transition going from excited to ground state, we can figure out the energy. And from that energy, we can backtrack using these equations that we learned, and we can figure out the frequency, or we can figure out the wavelength of that light that's emitted. So we can figure all that stuff out. I think there may be a couple of examples on that, but in the homework. I don't know why there isn't any here. But basically what happens is you can do the same equation for n equals 3, and you can calculate the energy. And then you can do the same equation for n equals 2 and calculate the energy. So, and you notice that if you put in n equals 3, this number will be lower. But keep in mind that it's negative. So it'll be a lower negative, meaning more negative. So meaning that if you have n equals 2, the energy will actually be higher, more positive. So, well, yeah. Wait. Yeah, whatever. But yeah, you could, and then you put in n equals 2, n equals 3, and then you subtract them. And then you could figure out the difference that way. Okay, so that's about it. I don't want to start with Heisenberg uncertainty principle. Yeah, okay, so one more thing. So it's important to mention this, which is the Heisenberg uncertainty principle. You're not going to need to know calculations to do this. You're not going to need to do this equation. I'm like 80% sure. I don't think you are. But basically, his uncertainty principle, maybe you've heard of this before, but basically it says that there's a limitation because electrons are moving very quickly and they're moving in these orbitals, but we think they're moving in these orbitals. Now, the Bohr model is just that. It's a model. It doesn't tell you exactly where the electrons are. And that's what Heisenberg was getting at, is that you can't know both the position and the momentum, meaning speed, because momentum is mv. So you can't tell both the momentum and the position of an electron at a given time because you can't know both of them. So because especially in electrons cases where they're really complicated. But we can talk about that forever. Let's just stick to the basics. And what this tells us is that, all right, we can't know the exact position, but we can have a probability distribution of the position, meaning something like this, where if you think the hydrogen's electron is in closer to the nucleus, which it most likely is, we can say that the electron is probably closer to the nucleus in this dark blue, but there's a chance, a small chance, it might be out here. So when we talk about these models and the energy levels and the positions, there is a chance we're completely wrong. That's what I'm trying to get at, is that these assumptions are just models that we make. So students and even when you're doing calculations, anybody really can understand it easier of what's happening, the phenomenon that's happening. Because if I started off this lecture saying that electrons are everywhere, but they have energy levels, you'd be like, wait, what the hell? But they're in approximate energy levels, but these energy levels or these positions of the energy level is a probability. So we can say chances are the electrons here are closer to the middle. And here's that probability distribution. We can say that most likely they're closer to the nucleus, which is distance from the nucleus. But there's a small chance, if you integrate this curve underneath, that the distance is far away. And that's maybe 1% chance. And so here's basically, if we're going to draw our energy levels, it would look like this. Chances are it's in energy level 1, but might be in 2, might be in 3. Very low chance it's in 4, etc. So we will end there, actually. Yeah, so next week we're going to start with quantum numbers, and that's actually a really interesting concept. Basically, the way I like to talk about it is a quantum coordinates of electrons. Based on the atom and the electrons, you can figure out its energy level, its angular momentum, its position in terms of if it's in a S, P, D, or F orbital, its magnetic properties, meaning if it's spinning left or right, and then also its spin if it's going left or right. But you can figure out these kind of coordinates of the different electrons. But anyway, so that's about it.